Welcome to the 7th lecture of Physics 221. Today we're going to start a new chapter, and this chapter is on complex numbers, and we'll be going beyond reals. And now, what are complex numbers? Let's first look at that. So complex numbers are numbers of the form a plus ib, where I is defined as the square root of minus 1, and a, b are real numbers. So these are your 1, 2, pi, square root of 2, and e's. But before we study complex numbers, I want to first try to think about why we study complex numbers. And to do that, we first have to know what numbers are. We have to go to the very beginning of numbers. So let's go on a little trip in history. Humans have since, long time ago, used numbers for counting. So the Egyptians, the Babylonians, and so on and so forth, they used numbers for counting. So the numbers 1, 2, 3, 4, and so on, these are what we call natural numbers. So these are the counting numbers. Now, the natural numbers are used for counting stuff. So naturally, you can define an operation on natural numbers. So addition is a familiar operation to us. So if we add natural numbers, we basically stay in the natural set of all natural numbers. And soon we find that we can also do subtraction on natural numbers. But doing subtraction leads us to negative numbers. So these, together with 0, form the integers. So there's an extension to the natural numbers. As the civilization progressed, people started to think about numbers, and they found that to have a complete picture of numbers, you need to have negative numbers. So these are the integers. And if you notice, z has nothing to do with integers. That's because the z comes from the German Zahlen, which means numbers. That's where the z comes from, if you're ever curious. And when you want to add a lot of numbers, you multiply, right? And you also have divisions of numbers. So if you have, say if I divide two numbers, I may not always get an integer. Sometimes I get fractions like these, right? So these numbers together, they're called the rational numbers because you can make ratios of integers. These are denoted by Q. Q as in quotient. Okay, but then if you combine these operations, these multiplication, subtraction, division, and addition, you have something called the algebraic numbers. You may have not seen these numbers before. So algebraic numbers are defined something like this. Algebraic numbers are solutions to algebraic equations. And algebraic equations, as you know, they only have subtraction, multiplication, addition, and exponentiation, some number times raised to n. This is basically multiplication done many times. That is exponentiation. So if I have an equation like x minus 3 equals 0, then x equals 3. Then 3 is actually an algebraic number. And similarly, if I have 2x minus 5 equals 0, then x is 5 over 2. Now 5 over 2 belongs to Q, the rational numbers, also belongs to algebraic numbers. So algebraic numbers is kind of like a generalization of Q, Z, and N. Now, if we take equations like this, x squared minus 2 equals 0, what is the solution? As you know, the solution is square root of 2, plus or minus square root of 2. Now, square root of 2, if you've taken in high school, you know that it's irrational. So it doesn't belong to Q, because square root of 2 cannot be expressed as in the form a over b, where a and b are integers, right? So what I'm trying to get at is that when you solve algebraic equations, you find new kinds of numbers. So suppose I have the equation x squared plus 1 equals 0. The solution to this is x equals square root of minus 1. Is this number actually defined? I mean, how does the square root of minus 1 make any sense? I mean, it's something to think about, right? And people didn't actually believe in, negative square roots. I mean, even back in the 16th century, there were some Italians who knew about square root of minus 1. People called Cardano. They used it, and there were other people. It's a huge fiasco. There's a Veritasium video about this, which I recommend that you watch. They used it to solve cubic equations. So cubics of the form x cubed plus bx plus bx squared plus bx plus c equals 0, equations of this form. And they actually saw that there are like numbers of this form, but they didn't really bother because they didn't make any sense. Okay, this is what the origin of imaginary numbers are. Like we've seen that, each of these numbers, natural numbers, integers, quotients, they have meaning in our everyday life. Like rational numbers, q, you can imagine them, if you're having a pizza, if you want a fraction of things, you see that there are real life uses of rational numbers. And so on with integers and natural numbers. But what about imaginary numbers? Even the rational numbers have uses, because rational numbers come up when you have triangles like this. So they have meanings. But what about imaginary numbers? Do they actually have any meaning? Well, this is where we come in with the usefulness of numbers. In physics, imaginary numbers are really, really useful. We use them in wave equations, solution to wave equations. We call them phasors. Phasors simplify calculations of dealing with waves, related to waves. And also in quantum mechanics. Quantum mechanics is impossible without imaginary numbers. The Schrodingers equation, which is the most important equation in quantum mechanics, is a complex equation. Let me show you how. You have the Hamiltonian operator times psi, the wave function, equals IH bar time derivative of psi. You don't need to worry about the meanings of psi and the Hamiltonian. This is basically telling you that the energy, the kinetic energy plus the potential energy equals E. This is the statement basically in quantum mechanics. Just with fancy equations. And people have proven, there are people who have proven experimentally and theoretically that quantum mechanics is impossible without imaginary numbers. And if you realize this, our reality is based on quantum mechanics. We cannot explain the universe without quantum mechanics, and we need complex numbers to explain the universe. So, complex numbers, we have to study complex numbers, the properties of complex numbers, because of this specific thing. Okay, also there's this really big theorem in mathematics, which is called the fundamental theorem of algebra. Which goes like this: any equation of the form x plus any polynomial equation of the form p of x equals ax raised to n plus so on until a constant a naught. So you have ax raised to n minus 1. Any polynomial of this form has n solutions of the form a plus bi in general. It can be purely imaginary or purely real, but in general it's like this. So the mathematics depends. The fundamental theorem of mathematics, one of them depends on the existence of complex numbers. Without it, mathematics is not complete. Okay, anyway, let's move on, let's study complex numbers now. Okay, so I've said that complex numbers are numbers of the form a plus bi with I equals square root of -1. Now let's look at the imaginary unit I. This is what we call the imaginary unit. Okay, so let's look at what happens when we square I. I squared is equal to -1. What happens when we cube I? When you cube I get -1 times I, which is -I. When I take the fourth power of I have I cubed times I, which is -I times I, which is 1. And when I take the fifth power of I, what do I get? I raised to 4 times I, which is 1 times I, which is again I. So I can look at a pattern here. So I start with I raised to 1 is I, and then I have -1, and then I have -I, and then I have 1, and then I have I again. So this pattern of 4 numbers, it's repeating. I, -1, -I, and 1. This is a pattern of the complex unit I. And this is useful for calculating complex numbers, operations with complex numbers. For instance, I can give you an example here. Suppose I want to calculate I raised to 2022, for instance. So what do? I cannot just do I times I times I 2022 times. That will take me a really long time. So what I do is I divide this and multiply this with 4. Why is that? Because I know that I raised to 4 is 1. Here I raised to 4 is 1. So this equals I raised to 4n plus some constant. Let us find these constants. So if I divide 4 with 2022, I have 4 times 5 is 20, and then 0, 5 plus 2. So I have I raised to 2022 equals I raised to 505 times 4 times I raised to 2, right? But we know that I raised to 4n is equal to 1 no matter what n is. So this must be equal to 1 times I squared, which is -1. So using this cyclic property, you can simplify calculations of complex numbers, operations with complex numbers. Okay, so let's do another example. Say I have I raised to k plus I raised to k plus 1 plus I raised to k plus 2 plus I raised to k plus 3. So I have 4 consecutive powers of I raised to I. So I raised to k. So what is this equal to? Again, I just take I raised to k common. I have 1 plus I squared plus I raised to 3. What is this equal to? Let's take the values of these from above. So we have I minus 1 and minus I. So I have I raised to k times 1 plus I plus minus 1 plus minus I. So I and I cancels out, 1 and minus 1 cancels out. So I have 0. So this proves you that the sum of 4 consecutive powers of I is equal to 0. So this is a neat proof. Anyway, enough with that. Let's now move on to how you can represent representing complex numbers. Since complex numbers have 2 parts, a plus bi, we give them names. So a is the real part and b is the imaginary part. You can almost think of a and b as a vector, and in a lot of ways it's true. Complex numbers form a vector space. and that's a fact. So you can think of real and imaginary parts as being the x and y planes, x and y axis. So x might represent the real axis, and y might represent the imaginary axis. This is what we call the complex plane, or argand, depending on how fancy you want to sound. So a plus b, so this is the real axis will give you a, the imaginary axis will give you ib. So you can think of this as a vector, ab, and it's perfectly valid. So this is what I meant in the beginning of this course, that vectors are not just arrows in space. There can be many things, and one of those things is a complex number. So let's now look at what you can do with complex numbers. You can add numbers, like in general, you can add, subtract, multiply, divide numbers. Can you do that with complex numbers? And how do you do that? So let's begin with complex addition. Suppose I have two complex numbers, z1 equals a1 and b1, by which I mean a1 plus ib1. I'm just using the same notation as we used before. And z2 equals a2 and b2. If I want to add z1 plus z2, I just add them like vectors. And if I want to subtract them as well, so I'm doing 2 in 1 now. a1 plus or minus a2, comma, b1 plus or minus b2. This is quite, ordinary. You'd expect this. So if you want to write this out like explicitly, I'll have the real part and the imaginary part, like this. This is z1 plus or minus z2. And the vector analogy, it actually makes complete sense. If I have two numbers, say I have a vector like this. By vectors, I mean complex numbers, of course. So basically, the addition, you can interpret the addition, like the normal vector addition. So z1 plus z2, it's like this. And you can imagine this like this. You have this is a1, and this is a2, and this is b1, this is b2. And it makes complete sense. So the vector analogy, is complete. Let's now move on to multiplication. For multiplication, I have a1 plus b1 times a2 plus, I'm missing an I here, ib2 equals z1 times z2. Now I'll just do this as a regular multiplication, like you would multiply to a quantity like this. So I have a1 a2 plus I a1 b2, I a2 b1, this with this, and then I have I squared, which is minus 1, b1 b2, and then plus I have a2 and so I'll also have a2 b1 and a2 b2, I guess. No, I'll have a1 a2 and then a2 b1 and then a2 a1 and minus b1 b2. Okay, I'm missing one term here. Okay, let's see which one is it. So yeah, it's b1 i2 and b1 a2. So if I separate the real and complex parts, I'll have a1 a2 minus b1 b2, comma, and the complex part, these parts, I'll have a2 b1 plus b1 a2. You don't have to memorize this. Whenever you have an expression, you just do it regularly, like regular multiplication. Well, moving on to division. Now, before I do the division, I want to like show you two quantities with complex numbers that you don't have in real numbers, two operations, the modulus and the argument. We'll see later that the modulus and argument have a real meaning in the coordinate system. They're not just, random operations. Modulus has a real meaning. So modulus, the first one is modulus, and modulus is denoted by having two straight lines like this around the complex variable z, and modulus is defined by z star z. Now what is z star? Z star is the conjugate, which is another operation that you don't have in real numbers. Well, how do I define a conjugate? The conjugate of a complex number a plus ib is simply, this thing star is simply a minus ib, right? So you're just changing this sign to minus, and if this was a minus ib, if I take the conjugate, I'll get a plus ib, because I'm just changing the sign. Okay, so the modulus is defined as z star z modulus squared. I'm sorry. Again, this relates to vectors. Like if I take a vector and multiply it with itself, I get the length of the vector squared. This is actually exactly that. And if I in a moment, if I show you what this equals, this will make perfect sense. So if I have z equals a plus ib, and if I take the conjugate a plus ib star, and one thing that you have to notice is that just like dot product, if I have a dot b and if I have b dot a, they're equal. This is one of the properties of dot product, and this is even true for conjugation. Like if I take z star z, it will be equal to z star. So the vector analogy makes even more sense now. Now let's calculate this quickly. I have a squared plus, okay, let's do it step by step. I have a plus ib times this conjugate, which is a minus ib, and I have, if I do this quickly, a squared plus iab minus iab and plus b squared, because I times minus I is plus 1 and b times b squared is b squared, and so plus iab and minus iab gets cancelled out. I'll have a squared plus b squared. Now if I had a vector a b and dotted it with itself, won't I have a squared plus b squared? I mean, it's exactly identical. So the modulus is in fact giving you it's giving you the length, or the magnitude, because length is for vectors. For a number, you just take the magnitude, right, of a complex number z. Now if I have a vector has, from your high school studies, you probably learned that vector is an arrow in space, and it has a length and it has a direction, right? Now we found the length of the vector, or the magnitude. How do we find the direction? And that's where the argument comes in. By argument, I don't mean like you're having an argument with your friend or your father or something like that. By argument, I mean the angle here, of course. This is the argument, the second operation. By argument of z, I mean the theta. Which theta do I mean exactly? This theta. From the real axis moving to the vector, this theta. How do you find theta? If you have a vector and you know the components like this, a and b, how do I know the theta? Of course I use the tangent. Tan theta is b over a. So theta equals argument of z equals tan inverse of b over a. As simple as that. And with this we covered the two operations, the modulus, and the modulus is this, z star z, which is equal to a squared plus b squared. Okay, we've now done the modulus and the argument. Now we can move on to division. The reason I had to give you the modulus before division, you'll see it now. Suppose I have two numbers, z1, z2, same as before, and I divide them. How do I, so I'll have, so let me just write what z1 and z2 are. z1 is a plus ib. z2 this time I'll just write c plus id for simplicity. Okay, so I have a plus ib over c plus id. Now I want to express it something plus I something else. I want to find these two numbers. So this is the standard form. Another thing that I have to tell you, the standard form of expressing a complex number is a plus ib. You cannot write a plus ib over c plus id. It's not the standard form. It's like saying, 3 over 6 equals 3 over 6. Oh, let's put it the other way around. I mean, that would make more sense. 6 over 3 equals 6 over 3. You have to simplify this, because people like to be specific. Just like that. So you need to express this in the standard form. Now let's see how you can do this. So the way we do this is by multiplying both the numerator and the denominator with z2 squared. And z2 only, not z1 squared, z2 squared. What will you get? I'll get z1 over z2 equals z1, z2 star z1 over z2 star z2. But z2 star z2, as we said by the definition we gave, is z2 squared. This is the modulus. And you have z2 star z1, which is a multiplication which you can easily do. Okay, what was z2? z2 was c plus id. If I take the conjugate, what will be the result? It will be c minus id. And what is z1? z1 is simply a plus ib. And what is the modulus again? It's c squared plus d squared, isn't it? As we said before, it's a squared plus b squared. So in this case, it should be c squared plus d squared. Now this is z1 over z2. And this is a simple multiplication. We can just do this quickly. This will be AC plus BD. This is the real part. You can verify this. I'm just doing this quickly. And I'll have I'll have BC first. BC minus AD. The whole thing divided by C squared plus D squared. So the numbers we wanted to find, what are they? So you'll have AC plus BD, and I just take this in each term. I'll just divide this C squared plus D squared plus I times BC minus AD over C squared plus D squared. This is Z1 over Z2. This is how you divide a complex number. Again, you don't have to memorize this, because you don't have to memorize this formula. You can just follow the steps. First, divide and multiply with the denominator, the conjugate of the denominator, and then find the modulus, and you'll get to this. I mean, you don't have to memorize the steps. Okay, so next thing that I want to tell you about is another way to represent complex numbers. And this is going to be familiar to you because, since we first said that the complex plane is like the Cartesian coordinates, like x and y, where x is the real part and y is the imaginary part. When we studied 2D coordinate systems, we also had the polar coordinates, didn't we? Oh, this is a terrible polar coordinate. One must be ashamed of this. Okay, let's draw a better one. So, haven't we taken the polar coordinate r theta? So we find that it's useful, to express the complex numbers in polar form. But how exactly do we do this? So if you remember, in the polar coordinates, the conversion was this: x equals r cos theta and y equals r sin theta, where r was the radius, right? I claim that x plus iy equals r. So if I'm moving to the complex numbers, I'll have an I here. Just that's the difference. Nothing else is different. I can just, use the same conversion, these relations, I can just use them here as well. There's nothing preventing me. I mean, there's nothing really different other than the I here, I sine theta. Now this is the polar representation of complex numbers, but there is a really, really nice trick that we can use to simplify this even further. And it's as follows. I think you might have seen this in high school, I don't know. This cos theta, this term here, cos theta plus I sine theta, is in fact equal to e raised to I theta. This is my claim, and I'm going to prove this to you in a moment. So basically z equals x plus iy. This is the standard form, and the polar form is r e raised to I theta, which is equal to r cosine theta plus I sine theta. Okay, so this is another representation in the polar form. It's a natural extension of the Cartesian and the polar coordinate system that we studied before. Right? Now I want to prove to you this relation, e raised to I theta equals cos theta plus I sine theta. And after this, we'll see, what mathematicians like to call, the most beautiful equation in math. We'll see if it's true, because in physics we really have more beautiful equations, in my opinion. Okay, we'll check it out. Let's start with, e raised to x. Now, if you have taken calculus 2, you remember that the Taylor expansion of e raised to x was like this. You have sigma n equals 0 to infinity, x raised to n over n factorial, which was 1 plus x raised to 1 over 1 factorial plus x squared over 2 factorial, and so on and so forth. You have the nth term. This goes on to infinity. This is the Taylor expansion by definition. I don't want to go into more details about the Taylor expansion. We'll just take this as a fact. If you don't remember this, just go ahead and look up your notes for calculus 2. Now what I want to do is I want to change x. Before x was real, now I want x to be complex. Actually, I want x to be imaginary. The difference between complex and imaginary is a really subtle one. So when I say complex, I mean a number of the form a plus ib, like this, a plus ib. When I mean imaginary, I mean a number of the form ib. This is the difference between complex and imaginary, if you ever thought about this. Okay, now let's continue. I want e raised to I theta, right? So I need x to be equal to I theta. Now here again, another fact will be useful. Which one? This fact that I told you, the powers of I, they're periodic. This one, they repeat like this. I have I minus 1 minus I and 1. This pattern repeats again and again and again. This is I raised to n, the pattern for I raised to n. I'm going to use this here in a moment. I'll show you how I'm going to use this. Okay, let's just substitute x equals I theta in the Taylor expansion. So e raised to I theta, by definition of the Taylor expansion, is 1 plus I theta over 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta raised to 4 over 4 factorial, and so on. You can imagine the rest, all the infinite terms in your head. Okay, so let's start computing these powers by the rule that we chose. So we have 1 I theta over 1. After I, what is the next one? I squared is minus 1, so I'll have minus theta squared over 2 factorial. What's after minus 1? Minus 1 is minus I, because the pattern goes something like this. Remember? I minus 1 minus I and 1. This is the pattern that is repeating. Okay, so let's continue with the pattern. So I have I minus 1, the next one is minus I, theta cubed over 3 factorial. And after minus I have 1 again, theta raised to 4 over 4 factorial. And after 1, I start here again. I have I. So I have plus I, theta raised to 5 over 5 factorial, and so on. Now, here comes the punchline. I want to combine the real parts, the real variables in here, and I want to combine the complex parts together separately, I mean. So what will e raised to I theta be? E raised to I theta will be, if I take the blue ones in here, I'll have 1 minus theta squared over 2 factorial plus theta raised to 4 over 4 factorial minus the next term I claim will be theta raised to 6 over 6 factorial, and so on. And the red terms, if I take the I outside, what will be the remaining inside the bracket? Inside the bracket, I'll have theta minus theta cubed over 3, this term, 3 factorial, plus theta raised to 5 over 5 factorial minus theta raised to 7 over 7 factorial, and so on, all the infinite terms. Okay, now if you remember, again, if you remember your calculus 2 lectures or the material, you know that this is the Taylor expansion of cosine theta. And this is the Taylor expansion. Let's make this red, to be consistent. Okay, so this should be the Taylor expansion of the sine theta. So we have just proven the relation e raised to I theta equals cosine theta plus I sine theta. Let's box this, because this is one of those equations that deserves a box. Now, if I take theta equals pi, what will I get? E raised to I pi equals cosine pi plus I sine pi. Sine pi is 0. Cosine pi is minus 1. If you do the graph, this is pi over 2. This is minus 1. So I'll have cosine pi is minus 1. So I'll have e raised to I pi plus 1 equals 0. This, to mathematicians, is the most beautiful formula. They've never seen the Maxwell's equations, I guess. Well, anyway, let mathematicians have their fun. Well, okay, so now I want to go back to the polar representation. Once I've proven this, I want to go back to the polar representation, because that's where we left off before we proved this. So we said that z in the standard form is x plus iy, and in the polar representation is e raised to I theta, where r is basically defined as the modulus, the square root of the modulus, or of the modulus squared. So I mean this is equal to square root of z star z. This is how r is defined, and theta is again the argument. So tan inverse of b, in this case it will be x, because z is equal to x plus iy, so it will be y over x. Okay, fine. Now I want to show you the implications of this. I've shown you, how addition, if you add two vectors, how they represent, they resemble the vector addition. Now I want to show you what happens when you multiply two complex numbers. So what's going on, like in the graph itself, when I do z1, z2. So suppose z1 was r1 e raised to I theta 1, and z2 was r2 e raised to I theta 2. This is in the polar form. So what will I get? I'll get r1 r2 and e raised to I theta 1 plus theta 2. Okay, first let me just recap what r e raised to I theta meant. R e raised to I theta meant you had a vector or a complex number. I mean, I'm going to use vectors and complex numbers interchangeably, so I hope you don't mind. This is r, this is theta, right? So in this case, this equation is telling me that if I multiply two numbers z1, z2, I'll get a number that has a length. I mean, I'll get a complex number that has a magnitude that is a multiplication of the magnitude of z1 and z2, and the angle is theta 1 plus theta 2, the angle of this vector and the other vector. Let's try and draw this. So yeah, I have theta 1, this is theta 1 r1, and I have theta 2 r2. So the result of this is as follows. I have a vector that is this length times this length. So you can imagine that it will be this long, and since theta 1 and theta 2 are being added, this will be moving this way. So let's imagine that this is not to scale, that the length is not perfectly to scale. I'll have a vector like this. I'll have a vector going like this. This is theta 1 plus theta 2, and this length is r1, r2. So in a way, multiplying complex numbers is like transforming a vector, like rotating it by some amount plus stretching it. Isn't this what we did? We just rotated it and stretched it by some amount. So this is like a transformation. And there is actually, a matrix associated with this, but we don't really need this like in this course. But if you're interested, there is a matrix that can do this. Okay, as an application of this, let's try and see, like z times e raised to I theta, where e raised to I theta is another complex number. If I multiply z with e raised to I theta, well, just e raised to I. No, iz. I want to show you what happens when I do z equals, iz. So I times x plus iy, this is equal to minus y plus ix. So I'm taking xy to minus yx. Now, if you remember our lecture on vector calculus, we said that dr was equal to dx dy, and if you want to take the normal, this is the tangent to the line, and if you want to take the normal dn, you did minus dy dx, if you remember this. So this is like rotating a vector by 90 degrees. And I can show you why this is the case. Like, if I have a vector like this, and if I multiply this vector by iz is going to be rotating this vector by 90 degrees, like this. This will be 90 degrees. This is iz. Okay, I can show you why. Because I equals e raised to I pi over 2. How is that? Because cosine pi over 2 is 0 plus I sine pi over 2. Sine pi over 2 is 1. This is 1. This is 0. This is 0 and this is I. So I'll have I. E raised to I pi over 2. Okay, so this is the interpretation of multiplication. The division is actually identical, except you'll have you'll have theta 1 minus theta 2 and r1 over r2. So the interpretation goes something similar. So if I have z1 over z2, I'll have r1 e raised to I theta 1 over r2 e raised to I theta 2. This is r1 over r2 and e raised to I theta 1 minus theta 2. So the interpretation is identical to multiplication. Okay, so this is the operations of complex numbers. We've done addition, we've done multiplication, division, and subtraction. We've also seen the operations, the modulus and the argument, which we said are identical to vector, the length of a vector, and the angle of a vector. Now we want to go and do some examples, I guess. Well, let's do some examples before I move on to the next big theorem, which is not a big. Which is not that difficult to understand that theorem. Well, let's do some examples. 3 e raised to I pi over 2. I'm given this number in the polar form. I want to convert it to x plus iy. How do I do this? So we said that r e raised to I theta, where r and theta are known from this. If I have this, then x equals r cosine theta from our coordinate systems. We discussed this in the coordinate systems, and y equals r sine theta. And how do I find theta? Theta is given. Okay, so in this case, r equals 3, theta equals pi over 2. So, x equals r cosine theta, so it's 3 cos pi, which is 0. And y equals 3 sine pi over 2. Sine pi over 2 is 1, so I'll have 3. So the number is z equals 0 plus 3i, which is 3i. I mean, we could have seen this from here without even doing the cosine stuff. How? I have a vector that has length 3. So it has a length 3 and it has the theta. This theta is equal to 90 degrees. So where does that bring me? That brings me here, 90 degrees here. And it's 3i. I can just look at it directly from the equation itself. This exercise, is just to get you familiarized with the two different notations of complex numbers. Okay, let's do an opposite example. This example, I'm given a vector like this: 1 over square root of 2 minus square root of 3 over 2, and I want it in the form r e raised to I theta. This is the polar form. They're giving me the standard form and they're asking me the polar form. Again, I go back to my definition. R is square root of x squared plus y squared, where x is this, y is this. So I'll have square root of 1/2 plus 3/4, because root 3 over 2 squared is 3/4. And this is simply going to give me, oh wait a minute, I have a mistake here in the question. Well, this should be squared here. 1/4 plus 3/4 is 1. And theta is tan inverse of y over x, which is equal to tan inverse of minus root 3 over 2 over 1 over 2. Now, this is a really tricky step. Why is that? Because, this will give me, you might say that this will give me tan inverse of minus root 3. The 2 and 2 gets cancelled. I'll get tan inverse of minus root 3. But the answer of this depends whether you have, minus root 3, tan inverse of minus root 3 over 1 is not equal to tan inverse of root 3 over minus 1. Why is that? Because, depending on what quadrant you're on the plane. So if x is plus, y is plus, you're in this quadrant. If x is minus, y is plus, you're in this quadrant, and so on. Both minus and x plus, y is minus. So it depends on which quadrant you're on, the angle you'll get is different. So you should really, really take care of this. And the calculator will not give you this answer. You have to decide yourself. If y is positive like this and x is negative, then which quadrant am I in? Y is positive, x is negative. I'm in the fourth quadrant, so the angle must be somewhere here. So if I get, the calculator might give you, for instance, for this example, the calculator is going to give you tan inverse of minus root 3. The calculator will simply give you minus, 60 degrees, I guess. But the real answer is 300 degrees because, we're in this quadrant. We're in the fourth quadrant here. Now in our example, I have y negative and x is positive. So in this case, I'm in the second quadrant. So what will be the answer? The answer will be pi minus 60 degrees. Pi is basically, let me write this in degrees. I mean in radians. Pi minus pi over 3, which is 2 pi over 3. So I'll have, okay, so I have r equals 1, theta equals 2 pi over 3. So z equals e raised to I 2 pi over 3. This is our answer. Okay, so now the next big theorem we have to study is Demovrous Theorem. Demovrous is a French guy, and this tells you, this is the statement of the theorem. The statement of the theorem is that z raised to n equals r e raised to I theta raised to n, which is equal to r raised to n e raised to I theta n. This is equal to r raised to n cosine n theta, because the argument here is n theta, plus I sine n theta. This is basically the statement of the theorem, and this is quite obvious, right? Because we've proven this, that e raised to I theta equals cosine theta plus I sine theta. We've proven this. So taking the power is really simple. Okay, so this is basically the statement of the theorem, and it's, as you can see, it's really easy, and it follows directly from the polar representation. Okay, let's do an example on this. So I have root 2 plus I root 2, the whole raised to 4. How do I do this? I mean, I can do this like, root 2 plus I root 2, I multiply it 4 times. That's a really lengthy process. Instead, what I can do is, I can change this to r e raised to I theta, so I can use Demovrous Theorem. Okay, so how do I do this? Again, r equals square root of x squared plus y squared, which in this case is square root of 4, which equals 2. And similarly, I have theta equals tan inverse of root 2 over root 2, which is 45 degrees, or pi over 4. So the number here is 2 e raised to I pi over 4, this whole thing raised to 4. And that, if you notice, is simply 2 raised to 4 e raised to I pi. And what does that give us? 2 raised to 4 is 16 cosine pi plus I sine pi. Sine pi is 0, so I'll get minus 16. That's it. I just did 1, 2, 3 computations instead of doing all the steps. So Demovrous theorem simplifies a lot of the expressions involving powers. This, as well as the one that we started with, which is the complex unit. When you multiply this, you have to remember this pattern. These two things will simplify most calculations for you, even in other courses, and I can testify to this. Okay, so now that we have a picture of complex numbers now, we know how to add them, multiply them, and do all the operations, usual operations, and we have a couple of useful theorems that simplifies calculations. Now we want to move into complex functions. Or functions with complex variables. Instead of having f of x where x is real, we'll move into f of z where z is complex. Now again, I'm returning here to multivariable calculus. This is similar to multivariable calculus, the next point that I'm going to make here. And that is that you have your input, the domain of the function, as we say in math, is a 2D, isn't it? Because you have the real part and the imaginary part, right? Because z equals x plus iy. Unlike real valued functions, complex numbers f of z can be thought of as a 2-variable function, right? So you have 2 inputs instead of 1. So the input is 2D. What about the output? I mean, f of z is in general another complex number. Let's call it, I don't know, what do I call it? Z sub f. Now z sub f has a real part and an imaginary part, doesn't it? So the output itself is again 2-dimensional because in general it's complex, so I'll have a real part and an imaginary part. Do you see the problem here? I need 2 dimensions for the input and 2 dimensions for the output. So in total I need 4D to represent the function completely, the input of the function and the output of the function. But we live, again, I hate to remind this to you every time, we live in a 3D universe, and I'm on a screen that is that is 2-dimensional, and I can only draw 1D lines. How do I represent a 4-dimensional function to you? That's the dilemma of life. Anyway, again, in this case, we use the same techniques, like we use contour maps like this, or heat maps. I don't know. We use the same techniques of representing functions. Okay, so that's basically how you represent complex functions, which is again, like multivariable functions that we've discussed before. Okay, so now there are actually three important functions that are quite, important for this course that you deal with a lot. These are e raised to z, the exponential function. In real we have e raised to x, but here z is x plus ey, so e raised to x plus iy. This will be equal to e raised to x times e raised to iy, which is e raised to x cosine y plus I sine y. Okay, simple enough. E raised to z is simple enough. And the next one is a complex number raised to another complex number. Now this is a little bit complicated, and to calculate this we need to first look at another function, which is len z, and len z is equal to len x plus iy. But is this really useful, len x plus iy? Doesn't seem very helpful, It doesn't give you any more information because we don't know what's len of iy, do we? I mean, we don't. So the thing that's going to be useful here is the polar form, len r e raised to I theta. Do you see why? Because len of AB is equal to len A plus len B. Okay, so using this I have len r, this is equal to len R plus len e raised to I theta. But what is len of e raised to something? Len of e raised to something is something itself, Len of e raised to x is x. So I'll have len z equals len R plus I theta. Now here comes the catch. Theta, what is theta? The values of theta, what are they? In polar coordinates we said theta was between 0 and 2 pi. But for complex numbers this is not the case. Because numbers, right? Numbers, they don't need to be unique. For coordinate systems we chose 0 to 2 pi because we wanted a unique coordinate for each point. But for numbers we can have many representations of a single point. This thing can be r0, r30 degrees. I can also add 360 to this, or in other words, if I have theta here, I can add any multiple of 2 pi, m times 2 pi, where m is equal to 0, 1, 2, and the answer will be the same. Why is that? So what I'm trying to say here is that if I have e raised to I theta, this will be equal to e raised to I theta plus 2m pi, I to m pi. Or let me write it like this. So I have theta plus 2m pi, where m is an integer. Now what is e raised to 2m pi exactly? We have cosine 2m pi, I am missing an I here, plus I sine 2m pi. What is this equal to? Now if you look at the curve of sine 2 pi is always stopping at 0, right? And similarly, if I take the curve of cosine 2 pi always stops at 1, right? If I repeat this again, it will stop at 1, at 4 pi. Similarly, and so on and so forth. So cosine 2 pi is always 1, sine 2 pi is always 0. So e raised to I theta plus 2m pi is e raised to I theta times e raised to 2i m pi, which we showed is 1. So e raised to I theta plus 2m pi equals e raised to I theta. So if I take the len of both sides, so if I take the len of this, I take the len of this, what will I get? I'll get I theta plus 2m pi equals I theta. Is this true? Not really. It's not true, but then the point that I wanted to get across to you is that len of another, since e raised to I theta equals e raised to 2m pi, if you add 2m pi to theta, you get the same vector, basically, same complex number. So if I have len e raised to I theta, I cannot just say that it's r e raised to I theta is len r plus I theta. You should consider the general case. So I should add 2m pi. So this is the general formula for len of a complex, the logarithm, natural logarithm of a complex number. Now we can deal with this, z1 raised to z2. So z1 raised to z2, how do we deal with this? We have x plus iy raised to x1 plus iy1 equals raised to x2 plus iy2. How do we even go about calculating this? First things first, we take len on both sides and we convert this to polar coordinates again. I'll convert these to polar coordinates, so this will be r1 e raised to I theta 1, this will be r2 e raised to I theta 2. So len of z1 raised to z2, what is that equal to? Firstly, that is equal to z2, this is the properties of len, times len z1, because len of a raised to b equals b len a. Well, if you remember this, good for you. If not, now you know. Okay, so we said that len z1 is z2. Len z1 is simply len r1 plus I 2 pi m plus theta 1, where m is equal to, m belongs to integers. This is len z1 raised to z2. But we want z1 raised to z2. Our question was z1 raised to z2. How do we do this? Well, we just raise both sides to the power of e. E raised to len something is something itself. So in this case, if I take e raised to this and e raised to this, what will I get? I'll get z1 raised to z2 equals e raised to z2. What is z2? z2 is x2 plus I y2 times, because this whole thing raised to you're basically multiplying these two, so we'll have len n plus 2 pi I m, depending on whether depending on the question, you don't need to simplify this further. You can just leave it like this. You can even take the real parts, e raised to the real parts together times e raised to I things together. That's it. You don't need to simplify things further. So those are the complex functions that you need to be aware of. I'm not going to do an example right now. I'm going to move on to another application, and that is roots, the square roots, the nth root of unity. So I'm talking about, I have square root of 1 is equal to what? Plus or minus 1, right? Because plus or minus 1 squared equals 1. Well, no. 1 squared plus or minus 1 squared is 1. So square root of 1 is plus or minus 1. And similarly, I want to find, the nth square root of 1. How do I do this? Well, again, I have to, express 1 in the polar form. So in the polar form, r is equal to 1 and e raised to I 2 pi m, where m belongs to integers. So m can be 0, 1, 2, 3, and so on. That's how I usually calculate the nth root of unity. I think I'll postpone the roots of unity to the next lecture, along with some examples of these complex functions. So the next lecture we're going to complete this chapter. So that's it for today. Thanks for listening, and I'll see you next time.